Alrighty, are you ready for this? So we're going to pick up where we left off last time in our review, which is free response question number 2 in the review packet for the kinematics portion of the or unit 1 of the AP uh, curriculum for Physics C. So the question here has. Oh, sorry, we were just admitting someone into the room. Okay, so we're picking up where we left off last time. That is question number 2, which involves a pair of motion detectors, a block, and another block connected to each other. And so it looks to me like we have essentially an outwind machine. And it reads, students design an experiment using blocks of adjustable mass to investigate friction using the setup shown. Block 1 of initial mass 0.44 kilograms is placed on a rough horizontal surface and connected by a string to block 2 of initial mass 0.2 kilograms. The string extends over the pulley that has negligible mass and friction. So here we do not need to concern ourselves with the rotation or rotational kinematics of the pulley, but we are going to have friction. And it appears that the masses will be changed somewhere along the problem, so we'll need to be careful to notice when that happens. So question A, or part A of question 2. Calculate the minimum coefficient of friction, mu s, that would keep the two-block system at rest. So they want us to calculate. They're not saying derive, but I think a big part of the work here is essentially a derivation for the expression. So what's going on here? Well, there are a couple of ways to analyze the system of connected masses. One way would be to isolate each mass and calculate the forces involved with this, mg, and then we have some friction here. And if they're not going to move, we're talking about static friction here. Okay. And then we have the other block, which happens to have the force due to gravity pulling it down. And we're going to call this force due to gravity 2. And here for the first block, I'm already losing consistency, but we have the force due to gravity 1. And then we have a tension, this problem. So because we do not need to worry about the rotation of the pulley, we can assume that these two tensions are going to be equal to each other. This would not be the case in a frictionless massless pulley because we would need to have a little bit of friction between the surface of the pulley and the string, assuming that's what they're talking about when they say frictionless. Sometimes they mean the axle itself is frictionless. But that tension would need to use friction to tug on the end here to create a net torque that would cause it to spin. So we're not going to worry about all that. Okay, so here we have some free body diagrams, and we can probably start doing a set of series of equations, but again, they said calculate, don't derive. So what is the main idea for this problem? Well, if this stays at rest, whatever's causing this to come down, aka the weight of mass 2, m2g, or the weight can also be thought of as the force due to gravity, is pulling it down. And over here, we're going to have some friction opposing the tendency to slide. And so if we look at this, the net force on the system, sure, there's tensions and other gravitational forces and normal forces, but first off, these tensions are internal forces. They don't affect the net motion of the object. I can't push on myself, essentially. And the normal force and the force due to gravity on block 1, they're going to be balanced out. And so we don't have to worry about that. So where do we start out with this? Well, we're going to go ahead and say that the weight of block 2, so the force due to gravity on block 2. And here we haven't really chosen a direction, but assuming this thing moves, we can go ahead and visualize this as being the positive direction of motion, downward for block 2, and for block 1, it's going to be to the right. And so looking at this, if we visualize our system here, the net force is eventually going to become the force due to gravity of block 2 minus the static friction force on block 1. Straight pen. And the net force on the system has to be equal to 0 because the system is going to remain at rest. It's initially at rest, and we wish to remain at rest, the velocity will not change. What does this tell us? The weight of block 2, or the force due to gravity on block 2, is going to be the force of static friction on block 1. Let's go ahead and make some substitutions for that. So I'm going to go ahead and scooch this over just to make a little bit more space. And in a second here, we'll pause just to hopefully help us catch up with what we've been talking about. Oops. I do see here I have a question in the chat, so I'll be addressing, or a statement in the chat, so I'll be addressing that here in a second. Oh, so here's a very important question. Can we use 10 for the acceleration due to gravity? Yes. On the AAP exam, you are strongly encouraged to use 10 for the acceleration due to gravity, just to facilitate calculations. So let's go ahead and expand this. Well, what is the force due to gravity? That's the weight, and that's the mass of the object. So that's going to be the mass of object 2 times g. And then the static friction force on block 1. Well, how do we calculate static friction? So static friction has this less than or equal to sign. And let me just go ahead and clear that up. And it's going to be less than or equal to the coefficient of static friction times the normal force. And what's the normal force? Well, at the end of the day, recognizing that this block 1 does not accelerate up nor down, just sideways, we can say that the normal force on block 1 is going to be equal to the force due to gravity, m1g. Okay. So what does this all tell us? That the static friction force is going to be less than or at a maximum equal to mu static times m1g. So we'll go ahead and substitute that in the actual space we were working with. So that becomes mu static, and we put the little subscript there so that we know m1g. So let's go ahead and talk about what are we going to do with this less than or equal to sign here. So here at the end of the day, we don't necessarily need to stress too much about it, because what this tells us is that at the end of the day, friction, this quantity here will be the maximum static friction available. Now, if we were to increase the coefficient of friction, that means that this allows us to have less static friction overall for the mass, or the mass we could get away with less mass here. But because we're constrained to using this mass as its normal force, or to press it into the surface to create this friction, we're going to go ahead and just leave it as the equal to sign here. And any coefficient friction value that we get out of this, that's fine. That's the minimum, because that's the largest amount of mass that we're putting on here. It's the mass of this block here. But if the experiment found out the coefficient of friction to be greater than this, well, that's fine, because that just tells us that we have we have a larger possible maximum static friction value, but we don't need it. And so we still satisfy the less than or equal to sign. All right, so without further ado, we recognize that the gravitational field strengths, or G's, or the accelerations due to gravity, cancel out. And at the end of the day, it becomes m2 all over m1 times g. Wait a minute, no, the g's cancel out, sorry. Silly mistake. I was gonna say the units don't check out there, what the heck? So in this case, what we find out is that the minimum, static friction coefficient will be given by this, and we can go ahead and populate this with a number. That's going to be 0.2 kilograms divided by 0.44, I believe. 44 kilograms. This should be a dimensionless number. Kilograms divided by kilograms cancel. And we go ahead and we find out that the static friction force is going to be given by, let's see here, 0.2 over 0.44. At the end of the day, you don't have to clean this up on the AP exam. You can leave it at this. If you wish to reduce it, you can leave it as 0.1 all over 0.22. We want to convert that into a decimal. You may, I don't happen to have my calculator here on me, but 0.0909, that's probably going to be 0.04545 or some kind of weird number sense trick there, recognizing that we have a half and the division by 11. So 1 second, we're going to admit another member here. Yeah, 0.454545. Okay, so I think I said 455. Sorry about that, but yeah. Okay, so mu s comes out to approximately 0.45 repeating. And I do apologize for the sloppy handwriting. I'm still getting used to writing with this latency and this setup, but hopefully it's not too much of an issue. And while you guys maybe read or write down the work that we've been doing here, I'm just going to rearrange this a little bit better just so that there's a little bit more flow to this, a little more legibility. So any one of these values is okay. And I'm actually going to erase the reduced fraction but non-decimal form just to kind of minimize the clutter. So you can either leave it as the values presented to you, or you could reduce it into a fraction. Just do recognize that this is not 0.450, it's 45 repeating. But we're good enough. And so at the end of the day here, thankfully, the acceleration due to gravity canceled. So let's go ahead and take a look at the scoring guide, see how they wanted us to tackle part A. Is this it? No, I think, all righty. I think it is this one here. Yep. Okay. All right. So sorry if it's a little dizzying there as I scroll through the pages, but I was just trying to quickly find where we were located. Okay. So this part was worth 2 points. Hopefully you recognize that I think I was doing a little bit more work than what the 2 points merit. So 1 point is for correctly evaluating Newton's second law equations for the system at rest. So recognizing that it's m2g minus the force of friction equals the mass of the system, m1 plus m2a. And so in my expression, I had already just canceled that and set it equal to 0. But let's see here if I even wrote that statement correctly. I just kind of wrote it. Yeah, here I left it as m, but it's a little ambiguous, right? What is this m? Well, if this is the net force of the system, this has to be the mass of the system. And so the mass of the system is really m1 plus m2. So be mindful of that. I was going through it rather quickly. I don't think they are looking exactly for that part, but technically I would dock myself that point and say I didn't apply Newton's second law equations correctly because I did not expand that. Just kind of ignored and just said, yeah, mass. Okay. So, and then the other point here is earned for correctly substituting for static friction into the above equation, recognizing that friction here is going to be the static friction coefficient times the normal force, and recognizing that the normal force is really just the weight of this object because we're on a level surface. We were not on a level surface, that would change some things. And so there we go. Oh no. Ooh, I'm gonna have to close OneNote. I think we're gonna start getting artifacts here. Give me 1 second. Let me pause recording here. All right, so there's that part. Let's go ahead and tackle question B now. And it reads, the coefficient of friction is such that when block 2 is released from rest, block 1 travels across the surface, okay, as predicted. And the acceleration of the block, or for each block, is recorded by motion detectors 1 and 2 as shown in the figure. And so so here is the graphs. But I also want us to reference, okay, how are these motion detectors set up? Well, motion detector 1 is recording the motion of block 1 as it moves away. And motion detector 2 will be recording the motion of block 2 as it moves towards it. So let's go ahead and see here. So the data for the motion detectors as functions of time, t, are shown on the graphs for each motion detector. The positive direction is away from the detector. One way we can think about it is, as it moves away, we are increasing the position or displacement from the detector. So things away are considered positive, and things toward or motion towards the detector would be considered negative. So this is consistent with what we expect. Block one is moving away from motion detector one. It looks to have an acceleration of, let's see here, each tick mark is, I believe, 0.2, 0.2, 0.4, 0.6. Nope, no, there's, sorry, 4. So it's going to be 0.25, my mistake. So about 2.25 meters per second squared. And yeah, we're getting some weird distortion there from the computer. Sorry about that. Motion detector 2 is detecting block 2 moving towards it. And as we should hopefully expect, the acceleration at this point is going to be 2.25 meters per second squared in the negative direction, aka towards it. They should have the same acceleration. This rope is not stretching. There's no relative motion between the blocks. They move as one entity. So they should have the same acceleration, just in different reference frames, positive and negative. Okay. So on the dots below, which represent the blocks while they are moving, I am assuming, draw and label the forces, no components that act on each block. Each force must be represented by a distinct arrow starting on and pointing away from the dot. So block 2 is going to be accelerating downwards. And so if you wish to pause the video here, for those of you watching the video to try it yourself, you're more than welcome to. So as we were saying, block 2 is accelerating downward. So we should expect a net force for block 2 acting downward. Or we should have more force due to gravity on block 2 than we have tension. I think that hopefully illustrates the idea. Okay. Block 1 is going to accelerate to the right. So we should expect a net force to the right. So the tension that is pulling it to the right is going to be greater than the friction acting on it. But because it is moving, this is no longer static friction. We're going to be precise enough and say this is kinetic friction, which my notation is force of friction, kinetic. I used to do lowercase f with a K for kinetic friction, but for whatever reason, one time I pulled students and they preferred the big F. So we know it's a force, and then friction tells us what kind of force, and then the subscript of that tells us what kind of friction, kinetic. Now we may be thinking, oh yeah, we're done here. But remember, we have to draw all the forces acting on the block in each direction. In this case, we do have forces in the vertical direction for block 1. It's M1G, or its weight 1, or force due to gravity on block 1, or the force due to gravity by the earth on block 1. There's several ways to illustrate or write that. Go ahead and just leave it this way. And because it does not bore through the table and only accelerates in the horizontal direction, we should not have a vertical net force. And so we should do our best here to draw our arrows of equivalent length. And you are allowed a straight edge or a ruler on the AP exam. So I strongly encourage you to take one so that you can use the lines as a reference for getting those lengths properly. These days, they usually put the free body diagrams with a grid so that you can draw the forces in relative length a little bit easier, but just in case they don't, it's handy to have one. I think that's it. Let's go ahead and take a look at the scoring guide, see what they were looking for part B. So examples of appropriate labels for the force due to gravity include Fg with a big G, with a little g, Fgrav, Mg, W, capital Mg, grav force, force of earth on block, force on block by earth, with these different subscripts. So hopefully here you can enjoy and feast your eyes on the different possibilities. Now, we have to be careful. Labels such as big G for gravity or lowercase g for gravity are not appropriate labels. So be careful here. Don't just use big or little g. And thankfully, we've never done that in my class. But in case you're one of the students watching this from the internet, just be mindful. I think your teachers should have probably mentioned that at some point. All right, the next part. F lowercase n, capital N, or F capital big N, normal force, ground force, or similar labels may be used for the normal force. Okay. So there were 4 points for this question, or this portion of the question. 1 point is earned for correctly drawing and labeling horizontal forces of friction and tension on block 1. Okay. 1 point is earned for correctly drawing and labeling vertical forces of weight and normal on block of mass M1. Okay. 1 point is earned for correctly drawing and labeling forces of weight and tension on block 2 of mass 2. And 1 point is earned for indicating that the gravitational forces on each block are different. Ooh, I don't think I get that point. I don't think I illustrated that, nor did I mention it in the explanation. But they did give us these masses, right? And we do know that if this thing, well, there is friction here. So it makes it a little easier to recognize that, yeah, this mass here could be different. Yeah, on a frictionless surface, it would be a lot harder to know which mass would be bigger, because on a frictionless surface, there's nothing to hold back the system. So regardless of the mass of the block on the table, if that table is frictionless, any mass would cause it to accelerate. But here they give us these masses. We know that they're 0.44 kilograms and 0.22. So did by sheer happenstance, did I have that somehow convey the idea? No, if anything, I said M2, or the weight of block 2 is greater than the weight of block 1. So that's a hack point there. So we're learning together. I usually do these live so that if I do make mistakes, I make them here with y'all, and you can see what are some of the common pitfalls. So sorry about that. I should probably polish myself off a little bit further, especially by putting these on the internet, but at least we're addressing it here. Okay, so the next part C. Calculate the coefficient of kinetic friction, mu k, between block 1 and the table. And we're going to assume that we're going to use these values for the acceleration. So if we think of the mass of the system approach, or a system of masses approach, we can kind of visualize this as one giant blob that was accelerating along, if you want to misuse terminology, this kind of line of action. The entire mass accelerates in these locations, in these directions. And so at the end of the day, we just have to worry about, okay, well, what are the forces on, for instance, this end of the blob versus this end of the blob, so that it keeps it from moving this way. The more proper approach to do this is to actually write out a system of equations. And this can depend or vary depending on your teacher's approach. For instance, what I like to do is I like to choose local coordinate systems that are consistent with what we are seeing. For instance, I would define down to be positive for block 1 and up to be negative. And ultimately, because these move in independent directions, horizontally and vertically, we don't have too much of a loss of consistency, because this is still consistent with saying that this is still positive. Okay, but I don't want to put A here because that implies that we have an acceleration sideways, which we don't. And then over here to the right is going to be positive, and we could also say, to keep it consistent, down is positive. Anyways, so this allows us to write our equations so that the accelerations, we don't have to think about them, and we can just plug in their magnitudes. Or not that we don't have to think about them, but we don't have to concern ourselves with their directionality being positive or negative. Because over here, the first equation we can generate is M2G minus the tension equals M1A. And the second equation for the acceleration of the system or motion is going to be for that of block 2. I'm sorry, block 1. Block 2 is over here. Block 1 is this equation. And that would be T minus the friction. I'm just going to go ahead and expand this for kinetic friction. Remember, that's mu times the normal force. The normal force is going to be M1G. And so again, they say calculate. So I'm just going to write it as mu K M1G equals M2A. And so when we do it with this approach, whatever accelerations we get here, we're just going to plug in their magnitudes because they are consistent with the direction of motion and the net force. Here I'm saying that the larger force is M2, the net force is downward. So M2 minus T is going to yield a positive value as its result. So the acceleration here would be positive. For block 1, T minus friction, well, I'm saying to the right is positive here. So this T minus friction would yield a positive result, and we would plug in a positive acceleration for that. And the reason why I bring this up is because in the graph above, they give us negative values for the acceleration of block 2, which is fine. I just figured this way makes it a little bit easier. Sadly, it's a little inconsistent with the information presented above. I'm going to talk about and evaluate it here in a minute as if they were negative. What would we do there? Okay. So let's say here you're doing it this way. Well, what do we do from here? How do we continue this equation? And so at the end of the day, we can do a system of equations, and there are several techniques on how to solve those. You can do substitution, solve for one variable, plug it into the other equation. Here we can recognize that because of the way we have set up our equations, we have a negative t term and a positive t term. So if we add these two equations, we get, and this may look weird. This seems like bad math, right? These are essentially vector equations. This is in the y direction for block 2, and block 1 is accelerating in the x direction. But at the end of the day, because we're already working with the magnitudes here, we can just go ahead and treat it as one system moving together. And so the acceleration of block 1 is the acceleration of block 2. They're moving in tandem. And so we don't have to worry about plugging in negatives here. And at the end, the result is still the same that we were talking about before. M2G minus mu kinetic M1G equals M2A. And what do we do with this? Well, we're almost there. We're trying to solve for the kinetic friction coefficient. And so at the end here, if we do a little bit of algebra, I need to move the M2G, or actually what we can do is we can swap the negative term in M2A so that it looks like this. M2G minus M2A. Oops, and I'm forgetting a term here, plus M1A. So I'm actually going to have to move these both over, minus M1A. So I moved over the M2A and the M1A because I added both sides. What happens when we add these guys is they cancel. And so we just get this minus that equals that plus that, because we really added the equations. We just happen to have a subtraction symbol there in the intermediate terms. And so this becomes mu M1G. And at the end of the day, sorry, I did not give myself enough space. Let's scooch over here, work in this void. And I'm going to also factor out some terms just to make it a little bit easier. This becomes M2G minus M2 plus M1A. And then I'm going to divide over the M1 and G to solve for mu. So M1G. And that gives us our friction coefficient. We can go ahead and start putting in some masses. M2 is 0.2. We can use 10 for G. And then over here becomes 0.2 plus 0.44 kilograms. And here, to minimize the visual clutter, especially if you're watching this on a screen with a small diagonal length, it's good, or just a small screen period. I'm foregoing the units just to minimize the clutter and just see what are the numbers that we're plugging in. And again, the numbers are not the important part as we have seen in physics. It's really all the work leading up to it. But just to make sure that we aren't making mistakes, right? Mass 2 was the one that's hanging, that's 0.2 kilograms. M1 is 0.44. And the acceleration that the system had, or individually, it was 2.25. And then M1 here is going to be 0.44 times 10. All right, and so that should give us our kinetic friction coefficient, which, let me grab my handy dandy calculator because I don't have a quick way of evaluating that one. It's 0.210. I'm getting approximately 0.12727 repeating. And so right now, in a second, we're going to go ahead and look at the scoring guide for this, make sure that we were on the right track. And so I definitely need to format these questions a little better so that we definitely have enough space. I think we can go ahead and shrink some of this part here. Oops. And then here, to make right of my previous mistake, let's go back and fix this guy to be even shorter. I think that delivers the point. Go ahead and scooch this work over. Oops. Okay. Anyways, let's go ahead and look at the scoring guide. I'll clean up the formatting later for those that wish to look at it through our OneNote here. And again, if you're wondering where we can find the work here, it's in our class OneNote. And so I've broken up the review. And so here is within the review, the scoring guide for today's free responses. So let's go ahead and see here what they were looking for. So here's the calculation they have. So 1 point is for correctly evaluating Newton's second law equation for block 2, where it's m2g minus t. And so they happen to do it this way as well. And then another one for combining the equations. It looks like they gave a second point. No, hold on. Let me read this. 1 point is earned for correctly evaluating Newton's second law equation for block 1. That's this one right here. And then another point is earned for correctly evaluating Newton's second law for block 2. Combining the two equations. Scoring note, both points are earned for a single correct Newton's second law equation for the 2-block system. So if you happen to jump into this form with, which I happen to call the blob method, which would yield this equation here. Let me get my pen. You can earn both points by applying this one. So I think that would be the faster way. And then 1 point is earned for correctly substituting for kinetic friction into the above equation. And so that's where we're saying that friction kinetic is going to be mu kinetic times the normal force, which is mu k m1g. And then at the end, they got 0.11. Oof, I happen to have made a mistake here. Oh, they are using 0.23 as their acceleration. I was using a 0.25. But everything else is consistent, right? It was 0.2 times essentially 10. They're also using 9.8, which changes the answers a little bit. But at the end of the day, this was the equation that we got, m2g minus m1 plus m2a all over m1g. It's the work, right? But let's go ahead and just make sure that we did that right. M2G minus M2 plus M1. Here they switch the order, but remember addition for normal numbers is commutative, really for just about any number. But I don't know enough about weird number spaces that aren't commutative or associative. I don't even remember. Anyways, and then all over M1G. Okay, so we're good on that one. Let's go ahead and look at part D here. And the only reason I say that is because the order of multiplication for vectors is not commutative, where if you change the order, you get the same answer. Sadly, a vector, and it also depends on how you multiply them for vectors, right? Dot or cross product. Anywho, lollygagging. Careful measurements determine that the coefficient of kinetic friction is larger than the value calculated in part C. Does the following explanation sufficiently account for the observed discrepancy? The horizontal table was not perfectly level before the experiment was conducted. Oh, okay, all right. The observed difference in the angle accounts for the differences in the expected and calculated values of mu k. Do we agree? And we justify our answer. Okay.
Okay, how about?
Oh, sorry, 1 second. All right, sorry about that. Okay. So let's go ahead and take a look here. So the real horizontal, the real coefficient of friction was determined to be larger. The actual value was larger than our calculated value. This is what we're calculating, but for some reason they made a measurement somehow and found out that it was larger than this. So what could explain why the coefficient, the calculated coefficient of friction was lower? Let's see here. So this is the calculated value. Well, we have a fraction. Maybe the overall numerator here was smaller than before. What would cause that to be smaller than before? Well, we have this subtraction term. And if the acceleration is larger than expected, then the calculated, or for that calculation, the overall numerator is going to be smaller. Maybe the weight got bigger, but I don't think that's going to happen. Right? The mass isn't changing of block one. The gravitational field strength, as far as we know, is not changing. So if I happen to incline the table and I didn't take it into account, then there was an above average larger acceleration, because not only do we have the acceleration from the system being pulled down by gravity, but we're also going to have a component of that g sine theta acting down the incline. Okay, so we have to be careful here with that. Oops. Okay, so it looks to me like this is in agreement, because if the table happens to be inclined down a little bit and we don't take that into account, we are shortchanging the expected measurement here. And so we're going to have a larger acceleration than what should have been. We have a larger acceleration than what should have been. That's going to give us a smaller numerator and therefore coefficient of friction. So I would say yes. And that would be my justification for the wording. Let's go ahead and see here how they worded in the College Board. So here's their example response. And this was worth 2 points. 1 point is earned for selecting yes and an attempt at a relevant justification, and then 1 for the correct justification. If the track is not level, the angle of the track must be incorporated into the equation for the acceleration, and this could account for the larger acceleration. So they're not even telling us whether, or we don't even have to say, was it tilted towards it or against it? We don't even have to explain that the acceleration there would be larger to yield a smaller calculated value. So more than anything, we just have to say yes, because that attack, or the angle of attack, sorry, the angle of the track would just have to be incorporated into the equation to accommodate that. Okay. So let's go ahead and look at the next portion here. The experiment is moved to a surface of negligible friction and run for 8 trials. In each trial, the masses of M1 and M2 are varied, while the total mass of the system, M1 plus M2, remains constant at 0.64. The data for the acceleration of block 1 as a function of M2 are shown in the graph below. Draw the best fit line for the data points. And so again, I strongly encourage you to have a straight edge on the AP exam with, so that you can actually draw a line of best fit. And so here I don't have a straight edge that works with my tablet or writing surface, sorry. So I'm gonna have to forego that luxury, but do not connect the dots. That's an important skill set for working with data points. Do not connect the dots. It should be straight in its curvature. And it looks to me like the data does go through the origin. So we can go ahead and have that line of best fit start from the origin and try to divide the data points equally above and below. And so we'll just run with this here. OneNote used to have features like insert shapes and the sort. Let's see here. We have something like that now. Yeah. Okay, so this version's a little limited. Okay. Part 2. Using the straight line, calculate an experimental value for the acceleration due to gravity. Well, shoot, how the heck are we going to do that with this data? So let's go ahead and look at the equation that we're working with. So when it's frictionless, I'm sorry, one second. We will resume here. Okay, so let's go ahead and look at the equation that was governing the motion of this. So we have 2 blocks, one hanging, one on a frictionless surface. And the equation for this is, well, we ask ourselves, well, what's causing the net, what's the net force on the system? Well, it's going to be M2G. And then there are no forces that are holding the system back because it's frictionless. So we just set that equal to the mass of the system, M1 plus M2A. And we're plotting the acceleration on the y-axis. Let's go ahead and move this term over through division. And we get that the acceleration A is going to be M2 divided by M1 plus M2 times G. And in this case, we are varying M2. So this is behaving like Y. This is behaving like X. So it turns out the rest of this is going to represent the slope. And so it looks to me like the slope is going to equal G over M1 plus M2. We are tasked with determining or calculating the value for G by using the slope of the straight line, or really the straight line. And here the slope is part of this information. So at the end, M1 plus M2 times the slope equals G. Let's go ahead and find out what that slope is. So it looks to me like this is maybe about, I don't know, 6.8 approximately at about, let's see here, 0.2, 0.25, 0.3, 0.35, 0.4. Okay. So then this is 0.45. Okay. So the slope of this is approximately 6.8 meters per second squared divided by 0.45 kilograms. And so let's see here what that yields. It's about 15.1. 15.1 meters per second squared per kilogram. Now, we're not done. That's just the slope. Now we need to turn that into this part of the equation. 15.1 meters per second squared per kilogram. And we were already told that the sum of mass 1 and mass 2 was held constant at 0.64. So that's 0.64 kilograms. So that cancels, that cancels. And essentially 2/3 of 15 is 10. And so using these values here, oops, made a mistake. We get approximately 9.67 meters per second squared. Let's go ahead and see what the AP Classroom here says. Oh my goodness, it went all the way to the top. All right. Almost there. There we go. So what values did they use? Well, they go to a value of about 6 over a run of from 0.15 to 0.45. So when they calculate their slope, they're working with this run and this rise. Okay. And our calculation happened to be using this run and this rise approximately. It is important that when you draw your line of best fit, you really calculate the slope of the line. If you notice here, the line is actually a little bit below this relative outlier. It's not really an outlier, it doesn't stick out that far. But hopefully you recognize that the line actually intersects at a vertical value of 6. You do not want to use specific data points for your slope calculations. You want to use line values or values that the best fit line passes through. Something that would have definitely been avoided had I had a better system to work with. But if you notice, for me, my line of best fit was approximately right on that value, which is why I went with it. I did not choose this data point. More specifically, it was the line, but I just kind of approximated it with that. Okay, so there's that question right there. And then part F. The students lift the end of the surface so that the surface is inclined at an angle below the horizontal, and the experiment for a mass of 0.2 kilograms is repeated. Would the acceleration of the system be greater than, less than, or equal to the acceleration of the system in the original experiment? So if we happen to lift the end of the table, it's gonna, not only do we have block 1 yielding the force that causes that system to accelerate, but now we have a component of block 1's, sorry, this was block 2. Let me get a little more precise here. So originally on the frictionless table, the only force causing the 2 blocks to move was the weight of block 2. But if we incline the table, now we have a component of the weight of block 1 also acting to accelerate the system. So because of this extra g sine theta term, we're going to have not just the acceleration as m2g divided by m1 and m2. As a matter of fact, we can even try to write it as m1g sine theta plus m2g. Those are the forces in the external forces on the system acting in the direction of acceleration, equals m1 plus m2a. And so we get that the acceleration is going to be g times m1 sine theta plus m2 all over m1 plus m2. Now, very important, we cannot factor out an m1 and an m2. They do not cancel out because not every term within the addition has an m1 and m2. It kind of looks like m1 plus m2 and they would cancel out, but m1 is being modulated by this sine of theta, so we cannot factor it out cleanly. Okay, so if we notice, the acceleration will be slightly larger than before, such that if we happen to like just tilt this perfectly at a 90 degrees, both blocks fall, the acceleration of the system is g, or 9.8 downward. Okay, so that's this question. righty. So question number 3 deals a lot more with forces than I thought would deal with. This is supposed to be kinematics, right? So I do apologize. This one also dealt with a lot with forces. So we're going to go ahead and skip number 3 here. And we're going to jump back to it when we do our review on forces. Because it'll be a little bit more appropriate then. But it's a really good question. So don't think we won't be coming back to it. Okay, question number 4 is a lot like question number 1, or at least the setup is, but it's not exactly the same. Again, we have a bucket with water in it, and it's going to be losing water through a hole, and it's going to start out heavier than the bucket heavier than the counterweight, and that's going to cause the system to accelerate. And eventually, when the bucket loses enough water, and the counterweight will have more weight than it, causing it to come back down. And so that's what this entire problem statement reads. The counterweight has a mass less than that of the full bucket, but greater than that of the empty bucket. At time t equals 0, the system is released from rest with the bucket full. At the same time, water begins to flow out of the bucket through the hole on the side near the bottom. The graph above shows the acceleration of the counterweight above its initial position as a function of time between the time t equals 0 seconds and t equal 1.2 seconds, where positive acceleration represents upward acceleration for the counterweight. So they are defining direction here for us. This is important because our answers must be consistent with this direction now. The bucket and counterweight continue to move long after this time. So what does this mean? So eventually, the bucket does return to its original location. And it appears, at least in the previous question, that was right around the time that they stopped the graph, but we're not going to assume that. The important thing here is that eventually the bucket keeps falling, the counterweight will fall more and more until the bucket ends up at the top. All right. So the question reads, at what time is the mass of the bucket and water equal to the mass of the counterweight, and explain your reasoning? Well, with these Atwood machine problems, we only have accelerations when there is a difference in weight on either side of the pulley. And we're going to ignore the torques and any of that motion of the pulley. You don't need to worry about it. It has negligible mass, therefore negligible inertia, rotational inertia. So if we look at this, if we consider our system here and the net force on the system, this is essentially the weight of the bucket and water minus the weight of the counterweight equals the mass of the bucket with water, the mass of the system, plus the mass of the counterweight times the acceleration of the system. So they want us to find out when are these two quantities equal? When are the weights or their masses going to be equal? If their masses are equal, their weights are equal in a uniform gravitational field. So here they want mass, not necessarily weight, but it's the same idea. M of the bucket of water times G minus the mass of the counterweight times G equals their sum of masses times the acceleration. So when are these two quantities going to be equal to each other? Well, if these two quantities are equal, then the acceleration is going to be 0. There's no net force. There's no acceleration. There's no difference in the weights on either side of the pulley. So they do not have an acceleration when the masses are equal because their weights are equal. And they cancel each other out in opposite directions. So the quick way to find this answer is to recognize, okay, when is the acceleration of the system 0? Which happens to be 0.4 seconds. Now, it looks to me like I am getting some artifacts here from OneNote. I'm going to go ahead and pause recording, and then we will resume here in a second. We're going to go ahead and resume recording. So we said that the time was going to be equal to 0.4 seconds because the acceleration is equal to 0. if the mass of the bucket and water equals the mass of the counterweight, the net force is 0. And the acceleration of the system will be equal to 0. And you don't have to put, I think, acceleration of the system, but I'm just being a little more specific. Okay. So let's go ahead and see here. So here's an example response, 3 total answered points. 1 point is earned correctly for indicating that time t equals 0.4 seconds with some attempt at a justification. So really important, if you don't attempt to justify, you do not get a point. So understand that if no justification is given, you're essentially not getting any points. Now here they are specifically asking you to justify. Sometimes you don't need to justify, but just be mindful of that. 1 point is earned for indication that it is at this time that the acceleration is 0 or some equivalent kinematic idea such as the bucket stops speeding up or begins slowing down. And the 3rd point is earned for indicating that the acceleration is 0 when the force is balanced. So this is when the masses are equal. Equilibrium implies forces balance and so therefore would get full credit for the scoring note here. And this is if the AP reader saw something along these lines. Here's an example response. When the mass of the counterweight equals the mass of the bucket water system, the net force on the system is 0 and the acceleration is 0. This occurs at t equals 0.4 seconds. All righty. Let's go ahead and look at the next part. At what time does the counterweight reach maximum height? Justify your answer. So let you guys look at this graph here, and I want you to determine, when is this going to be at its maximum height? And if you're thinking 0.8 seconds, you're 100%. I don't know, we're going to find out, but let's see here. So what's the thought process? Well, it has been speeding up this entire time. The counterweight had a positive acceleration, so it had positive velocity change upwards. And so all of this time here, or all of this graph from 0 to 0.4, if we get its area, that graph is going to give us the change in velocity. So at 0.4 seconds, it stops speeding up, but that does not mean it stops slowing down. Remember that if I throw a ball up, it's going to keep climbing up until it loses all the velocity I gave it. So if we get the area of this, this tells us that we have a positive velocity upwards. After 0.4 seconds, the acceleration is negative, which is going to create a velocity change in the opposite direction, and it's going to slow it down. And if we look at this, the slope is constant. So if it took 0.4 seconds to stop speeding up, it's going to take another 0.4 seconds to slow down and come to a stop. Because remember, the idea is for a projectile or anything accelerating, if it reaches the maximum extent of its motion, that means that the velocity has become 0. So this positive delta V and this negative delta V have to be equal to each other. And so we have this line here, and so that should be 0.8 seconds. And we could say the area is the change in velocity for the counterweight. The maximum height occurs when the final velocity is 0, occurs when the velocity is 0. If it started from 0 and it finishes with 0 velocity, the overall change in velocity has to be 0. So we could say if VI equals 0 and VF equals 0, delta V equals 0. So we need a net area of 0. A positive area. And this would occur at 0.4 seconds. I mean, at 0.8 seconds, sorry. Well, let's just scooch this whole thing over. Oof. Okay, so there we go. Let's go ahead and look at the scoring guide. So the next question will be worth 3 points. 1 point is earned for indicating that t equals 0.8 seconds with some attempt at a justification. 1 point is earned for indicating that at this time the system has 0 velocity. And then 1 point is earned for explaining why the velocity is 0 at this point, either by citing equal positive and negative areas up to this point for the graph, or stating that the average acceleration is 0 at this point. And so here's our example response. At the highest point, the velocity will be 0. From t equals 0 to t equals 0.4 seconds, the counterweight is increasing in speed. And for the next 4 seconds, it is decreasing in speed at the same rate. So at t equals 0.8 seconds, the speed will again be 0. Very nice. Let's go to the next question. The students model the velocity of the counterweight using the function v of t equals 1.2t minus 1.5t squared for the time interval of 0 to 1.2 seconds. Note that positive velocity represents upward velocity for the counterweight. And the question here reads, is it plausible that this function could correctly model the velocity during this interval? Why or why not? Well, let's see here. At 0 seconds, the velocity of the counterweight should be 0. And so it looks to me like, well, at least the first part is consistent because it is released from rest. So the velocity of 0 according to the function equals 0. So that's consistent. It is released from rest. That's not enough though. Let's go ahead and continue analyzing this. As a matter of fact, let's see here. Do we have information about the velocity? And I don't think we have that bit of information. But we do know that the velocity at 0.8 seconds should be equal to 0. So let's see here. Let's find out what is the velocity in the equation at 0.8 seconds. Well, that's going to be 1.2 times 0.8 minus 1.5 times 0.8 squared. And I think here it's in our best interest to type this into the calculator right away so that we don't make mistakes. 1.2. I mean, I think we can number sense it, but either way. And lo and behold, we get 0.96 minus 0.96. That's a big old 0. So that checks out because the velocity at 0.8 seconds we determined has to be 0. So that's good. It's looking good so far. Now let's go ahead and check the final state of our velocity at 1.2 seconds to see if it's valid not only at the beginning of our interval, at some point within the interval, and then at the later part. And so if we look at this, this becomes 1.2 squared, that's 1.44 minus 1.2 squared, that's 1.44 times 1.5. Oops, sorry, my pen spazzed out. We get a velocity of negative 0.72 meters per second. I think we should hopefully expect that by now it's moving downward, right? It reached its maximum extent after 0.8 seconds. So it's going to be moving down after this point, and we should hopefully expect a negative velocity. So I think that this correctly models it within the time interval, and these are some good reasons for it. I do have a problem with this though. This does imply that the acceleration would continue to grow indefinitely in the downward direction. But once the bucket is empty, the mass no longer changes. And once the mass no longer changes, the acceleration is not going to change. It's going to be fixed. As a matter of fact, at the end of the day, the acceleration is going to be the mass of the counterweight minus the mass of the bucket. There's no water in it anymore. All over the mass of the counterweight plus the mass of the bucket times G. So as the water starts to drain, we do have a changing acceleration, but once that water is drained out, the bucket itself still has a mass and an inertia, which is affecting the overall acceleration. So I would say yes, and by and large, it works. Part D says, explain why this function does not correctly model the velocity of the counterweight for a long period of time. So that would imply that the velocity would be continuing to grow. If we took the derivative of that, sorry, I kind of jumped the gun here, because even though this is an equation for velocity, if we take the acceleration or the derivative of it to get the acceleration, that's 1.2 minus 3t. So this is why I was saying it was going to continue to grow indefinitely for the acceleration. This implies that we're going to have an infinitely possible negative acceleration, but not the case. Okay. As a matter of fact, at about 1.2 seconds, I'm sorry, I was thinking something else. Never mind. Okay. So let's go ahead and see here what the College Board was looking for in these two parts. I kind of just answered them together and I didn't really write much, but hopefully you were able to follow along on that statement. So let's go ahead and see here. So 1 point is earned for a correct statement about the given velocity. 1 point is earned for correctly connecting the velocity function to a relevant feature of the graph or a description of the motion. Because the prompt asks, is it possible a student can also earn points for an explanation of why not? Well, at t equals 0, the derivative of v of t gives 1.2 meters per second squared. And so I think there, when I was referencing the values, I made that mistake, but yes, okay. We needed to take the derivative to say that the oh wait, well, I was talking about the velocity. The velocity is 0, but the acceleration is also consistent here. We took its derivative and we applied t equals 0 to that expression. We would get an initial acceleration of 1.2, which is what the graph was saying. Well, not exactly, right? Because they don't give us values. I was thinking that right now, but we could go ahead and assume that, okay? Connecting the graph, the answer doesn't address whether the model is right, but it does connect to the graph, so it earns full credit. So we could say the derivative of the velocity has a 0 at t equals 0.4 seconds, which is consistent with the acceleration graph. Also, for times less than 0.4 seconds, both the function and the area under the graph have positive values. Thus, it is plausible that this function could model the velocity. So there we go. All right. D. So what were they looking for here? So this is where we were disagreeing with the explanation. And 1 point is earned for a statement that includes that the velocity function allows the acceleration to increase without bound beyond a magnitude of 9.8. At most, it should be 9.8. It is in free fall. So it cannot grow indefinitely. And not only that, I mean, the acceleration really is going to be different. It's going to be given by that expression I wrote on the previous page. And then the other point here is earned for a statement that the velocity function will be linear, or that acceleration will reach some constant value because the bucket has run out of water and its mass will stay constant. That was the second part I was referring to right now, where I drew that or wrote that expression. Okay. And here is their example response. The velocity function is quadratic and the acceleration is the derivative of velocity. So this function allows the magnitude of the acceleration to increase as time increases. However, Once the bucket loses all its water, the mass of the system and the net force acting on the system will be constant. So the acceleration will stop increasing at some value less than g equals 9 or less than g equals 9.8 meters per second squared. Okay, so let's go ahead and look at part E, and I think we're in the home stretch for this question. So the students are told that the counterweight's mass of 15 kilograms is, I think we have a typo there, is 15 kilograms, and the mass of the bucket with water in it is approximately given by the equation m of t is given by 1.28 t squared minus 9.34 t plus 18.65 kilograms for t less than or equal to 3.5 seconds. The students also know the initial heights of the bucket and the counterweight above the ground. Assume any action-reaction forces between the bucket and the water draining are negligible. Explain how the students could use the information along with the velocity function to calculate the total mechanical energy of the system consisting of the bucket, the water in the bucket, the earth, and the counterweight at a time t equals 1.2 seconds. So if we look at this, there's a couple of ways to do this. If we know the heights, we can go ahead and measure their relative positions as they change to get the change in potential energy. Because the total mechanical energy of the system, well, this is the complicated part. In my opinion, this is an open system because the water is going to leave the bucket, therefore changing the mass of the system. But at the end of the day, if we want to assume at 1.2 seconds, well, what was so special at 1.2 seconds? Well, at 1.2 seconds, where's our velocity function here? Where did they write it? I'm jumping back and forth. Okay. That's negative 7.2. So we're going to assume that maybe that's, well, no, it's already moving down. I guess they just want us to use that time. So what do we do with this? Well, we can take the integral of this. If we take the integral of the velocity function with respect to time from 0 to 1.2 seconds, that's going to give us the displacement. So if we know the displacement, we know that the change in gravitational potential energy is going to be relative, or that change is going to be relative from their location. So let's say we found out the displacement is, I don't know, 1 meter. So if this goes up by 1 meter, this goes down by 1 meter, and we can compare the mass of the counterweight with that of the water in the bucket. Because at the end of the day, the mass at 1.2 seconds can be determined. So we know what the immediate mass of the system is at that point. And I'm trying to right here see how I could represent that, because I feel like all these ideas are kind of scattered about right now. But if we integrate this from 0 to 1.2 seconds, we find the displacement of these blocks. One of these is going to gain gravitational potential energy. That's going to be the bucket and the counterweight, because at that point, the counterweight had been moving up. So we're going to assume that up to that point, it has, oh, no, because by 0.8 seconds, it's already reached the top. Let's say for whatever reason, it's going to have less acceleration. So you know what? We're going to say that it's moving down, but it's still going to have an overall upward displacement. We know that at 0.8 seconds, the counterweight reaches the peak. And the initial acceleration of the system was greater. So it's going to take more time for this object to drop back down to its initial position. Even though it has a negative velocity at 1.2 seconds, it is moving down, but it has not moved all the way downward. So what's the idea? We can find the gravitational potential energy. So we'll say find UG of the counterweight. At 1.2 seconds. Well, that's going to be the mass at 1.2 seconds because that is changing times g, which is constant, times whatever the height of 1.2 seconds is. And the height of at 1.2 seconds could be determined by integrating this function. Or the change in height here, sorry. Find. Sorry, I'm trying to rush this. I apologize, y'all. I'm making mistakes. But I understand it is late. So what's the other thing? We can find the gravitational potential energy of the bucket. Sorry, the counterweight has a constant mass. That's going to be the 15 kilograms. It's just the height that is changing. The bucket is the one that is having a variable mass of the bucket and water. And that's going to be the mass at 1.2 seconds times the acceleration due to gravity times the change in height after 1.2 seconds. And then we need to find the kinetic energies. So 3, find kinetic energy of the counterweight and the bucket. And I'm just going to go ahead and just write those steps here in as one step. And I don't know why I'm hyphenating counterweight before I hadn't, but so it goes. And the bucket with water. Sorry, I'm making a lot. Okay. And how are we going to do that? Well, kinetic energy is 1/2 mv squared. So that's going to be for the counterweight, the kinetic energy of the counterweight, that's going to be 15 kilograms times the velocity at 1.2 seconds quantity squared over 2. And the kinetic energy of the bucket and water is going to be the mass at 1.2 seconds times the velocity at 1.2 seconds quantity squared. Okay, all over 2. So all we have to do is calculate all these quantities, and then we have our answer for the total mechanical energy. Because again, the total mechanical energy is the sum of kinetic and potential. So that would be the way. We just have to explain how to do it. We don't actually have to do it. Let's look at the scoring guide here. So 1 point is earned for explaining how the equation for the mass of the bucket and water could be used to calculate its mass at the given time, or for explicitly stating that the mass of the bucket and water will be about 9.3 kilograms. The next point is earned for indicating that the student should take the integral of the velocity function to get position. Another point is really going to give us displacement, but because the students know the initial position, they will know the final position. And so they can really generate a function of position from that point. 1 point is earned for explicitly stating the limits to be 0 to 1.2 seconds, or for using an indefinite integral and indicating use of the given initial conditions. 1 point is earned for stating that the positions and masses of both objects could be used to find their potential energies relative to some arbitrary 0 point. Or stating that the velocities and masses of both objects can be used to find the kinetic energies. And the last point here is earned for clearly stating that the mechanical energy is the sum of the kinetic and potential energies of the system, which I mentioned at the end, but I didn't write down. So maybe a point for that one. A student who only discusses one of the two objects loses the 4th point, but could earn the 5th if they sum kinetic and potential energies for that object. Okay, and then so here is their example response. And so I'll let you guys read over that. We're going to go ahead and stop the recording here. We're going to go ahead and call it a day.